Okay. Would appreciate if as many of you can turn on your videos as possible, as I mentioned. All right, so any questions overall on how the class is going and how things have worked? Homeworks are due today, just so you know, or theoretically like 3 minutes ago. Make sure you upload it, let's just say before the end of class, if you have not already.
So I had a question over the homework on more on like the submission format, because for kinetics, there was like a cover sheet that we had to attach. And then it also says like ChE421/421. And so I was wondering, like, do we have to do that for this class too?
Okay, so the question over Zoom, could you guys hear that? The question over Zoom was there was a cover sheet in kinetics that you have to attach onto all the homeworks and stuff in kinetics. Is that true? Nod your heads.
Right.
Okay.
And on the cover sheet, it also said 421, which is this class. So I was
Yeah,
like,
I'll give you guys a little bit of history of where that. When we were turning things in on paper, we required all of you guys to write your solutions on like an 8.5 by 11-inch piece of paper, like on white paper and stuff, and then to attach a cover sheet so that there were nice little packets that the TAs could grade very easily. We decided at the beginning of this class that that doesn't really matter if you're just going to submit PDFs online anyway, and so we stopped with the cover sheet thing. I can't tell you what's going on in kinetics nowadays, but because you guys are just submitting stuff over PDF, the cover sheet doesn't really matter to us. Canvas already makes it very clear what is what and keeps everything organized, because you can't. Very hard to have like loose papers in PDF form on Canvas, so we don't really care. If you want to submit a cover sheet, then sure, we don't really care. So.
all right, thank you.
Okay, really sorry about the audio thing, guys, but hopefully I can repeat questions and again, remind me if that doesn't happen. We've been talking about vector calculus. That's what we started with last lecture. And so we're going to continue that a little bit. Last lecture, we introduced things like, here, I'll just go here a little bit. We introduced things like what is the gradient? What is the divergence? What is the curl? Stuff like that. And Laplacian, and then we proved some relationships. We were able to do that using our newfound knowledge of index notation. And then we started talking about the physical meaning of some of these vector derivatives. So gradient and divergence. On the way, we were able to derive a key relationship called the divergence theorem that we are going to use later on in fluids, as we start to go into fluids, which we're going to get into a little bit later today. And so today, I just want to continue this discussion by starting to talk about the physical meaning of curl. Okay, so here we go. Okay, so just like how before when we were talking about gradients and divergences and stuff, we drew a little picture. For the divergence, if you remember, it was like a little box, and we're figuring out what's the flux of this vector field going in and out of this box. For gradient, we were talking about like what's the value of the scalar field at any different location within that gradient, right? For a curl, what makes the most sense is, let me give myself a set of axes again. One, two, and three. What makes the most sense to discuss is a rectangular shaped, you can call this a surface. And this rectangle has 4 sides, obviously, and 2 different dimensions. There's a delta x2 in this dimension and a delta x1 in this dimension. Okay. And what I want to ask is, what is the contour integral of f dot t ds? Okay. Evaluated as you walk around the surface. And by convention, we're going to walk around the surface in this direction. Okay. And then by convention, if you walk around this surface in this direction, then we also think about a normal vector to the surface that goes like that according to the right-hand rule, because it looks like this, right? Okay. And so C is this contour, right? I'll just write out explicitly. T is tangent. I'll say is a unit tangent to our contour C, and n is the unit normal. Okay, and so what we have here, let me just write out again. We have a rectangle centered at the position x1, x2, x3, and the area is delta A equals delta x1, delta x2. Okay. This is analogous, of course, to like we were talking about that box centered again at x1, x2, x3 and stuff, and then had a volume as well, right? And what we're trying to calculate now is this weird sort of contour line integral as we move around it. And so just like before, when we were dealing with a box where we had like a flux going in and out of this surface or of this volume, now we need to basically break this structure up piecemeal and then calculate what the value of this integral is on all the sides. Okay. So I'm going to call this side over here side A. Okay. And then we're going to walk around. So this is going to be side B here. This is side C. And this is side D. Okay. And so let's go ahead and talk about how, like, what the value of this integral is going to be. Okay. So on side A, okay, our tangent. Does anyone know what the value of this, what this unit tangent is going to be? Anyone over Zoom or anyone here? Just say it, and I'll repeat it if anyone gets it right. What is the tangent vector along this position right here? Just E1, right? It's a unit vector that's tangent to this rectangle, okay? And because of the arrow pointing in the direction that comes towards you, then it's going in the plus E1 direction, or the plus 1 direction, okay? And so what that means then is that F dot T is then just going to be F1. Okay, and so this line integral is just equal to F1, right? And that's F1 evaluated at x1, x2 minus delta x2 over 2, x3, multiplied by the length of that rectangle, of that side of the rectangle, delta x1. Okay, and this minus delta x2 over 2 is just because, well, you know, the rectangle is centered at x1, x2, x3, and so we have to shift it over by a factor of delta x2 over 2. Okay. Taylor expansion, we've done that already a lot in this class. And so what we have here then is F1 at x1, x2, and x3 minus df1 dx2 times that. Okay. We can do the same thing for side B. It's pretty analogous. I won't pause to ask you guys what this is. You guys can hopefully see that the tangent vector now is E2. Okay. And so that implies that F dot tangent vector here is equal to F2, right? And so the line integral here is just equal to F2. Now, we're not going to evaluate this at x1 anymore. It's going to actually be right here, right? It's going to be evaluated at the center of this line, and that's a distance of delta x1 over 2 offset from here in the plus s direction, right? So it's actually going to be evaluated at x1 plus delta x1 over 2, x2, and x3. Was there a question? So the question was, is f here a tensor because it's capital, right? The answer is no, it's a vector. The one underline just means it's a vector. You could theoretically apply all of this to a tensor again, but in this case, we're only talking about a vector field. Okay. Yeah. By convention, like I'll try to make the thing that you should pay the most attention to is the underline, the number of underlines, basically. Okay. Okay, and so this was the how we calculate the contour length or the contour integral for side B. Okay, and then again we can Taylor expand this as well. Seeing something in the chat. Okay, cool. There's going to be a big delay because I'm like doing a lot of different things and I'm not necessarily going to pay attention to the chat all the time. If you have a question, just yell. Unmute yourself and yell, and I'll repeat it to everyone and stuff like that. Yeah. You guys are sorry about the confusion. F is just a vector field basically. Okay. Here we go. And so by analogy, from above, we can do Taylor expansion again. Like that. Okay. And the other two sides are actually pretty analogous as well. Okay. Just for completeness, I'll go ahead and do all of them. Side C, this one's just a little bit different. It's because here the tangent vector is pointing in a different direction. There is a directionality to the way that we're doing this. And so here the tangent vector is going to point in the negative E1 direction because here this one goes, into the page, okay, or into the board. Okay, so this is going to be negative E1. Okay, and so that implies that F dot T here is equal to negative F1. Okay. All right, and so, this is essentially analogous again. F dot T ds is equal to negative F1, X1, X2. Now it's going to be plus delta X2 over 2. And sorry, not delta here. X3 times the length is delta X1. You guys can hopefully see why this is a plus delta X2 over 2. It's because we're offset over in this direction now. Okay. And so then if we do the Taylor expansion, we get this. Like that. Okay. And then now we can just do side D. I'm going to skip a couple steps on that one. But hopefully you guys will believe me when I tell you that the value here, that the answer here is just this. Okay, and if you don't believe me, go home and just figure it out yourself. Okay? But it's essentially analogous. All right, and so what that means then is I can add together all four of these terms. I need to add this to this to this to this. So I'll just put a little star here. I'm going to add together all of these. Okay, and so that means that the overall thing that I care about, this contour integral, is then, when I add these together, it turns out that this F1 evaluated x1, x2, x3 exactly cancels this negative F1. So that's gone. That's kind of cool, right? And this F2, sorry, there's a 2 here. This F2 exactly cancels this negative F2 as well. Okay, and so those guys are gone. And so all I'm going to care about are these terms on the right. Okay, and for all these terms, what I get here is a negative F1 dF1 dx2. Here I also have a negative dF1 dx2, and so there's a factor of 1/2 in each one. So overall I get one factor of minus dF1 dx2. And then over here I have a dF2 dx1 plus another dF2 dx1, 1/2, and so a full dF2 dx1, all of the terms have a factor of delta x1, delta x2 in front of it. In this case, it's delta x2, delta x1, and then in this case is delta x1, delta x2. Okay, so that means my overall sum looks like this. Okay, our video just went out for a second in the room. Is everyone on Zoom still able to see the videos? Still able to see the screen? Okay, cool. And the room still seems to be doing okay for a second now. Okay, so that's the answer. This is the answer right here. And what you might notice about the curl, if you remember a little bit about what the curl is, I don't expect you to because the curl is kind of confusing. It's like a lot of derivatives minus derivatives and stuff like that. But you might believe me if I tell you that this relationship is true. I would never lie to you guys, all right? Okay, so this difference in derivatives is the z component of the curl of f. Okay. Now there's nothing that says that. Sorry, I'll scroll down to that in just a second. I just want to point to this one again. There's nothing that says that that I happen to draw this in this sort of orientation. I could have drawn it in another orientation. I could have had the n pointing in a completely different direction or something like that. So there's nothing special about this E3, the fact that n here happens to be equal to E3. And so what that means is that, just in general, I'm going to divide through both sides. I'm going to divide both sides of this by delta x1, delta x2, and again, let those two values go down to 0. What that suggests then is that n dot curl of f is then equal to the limit as delta a goes to 0 of 1 over a that. Okay. And so what this means is that the physical meaning of the curl of f is basically the curl of f. It's how much the vector field curls. If I were to integrate around a circle, it's how much it's basically how much the vector field actually follows my integral or something like that, right? And then the direction of which the curl is maximized, or the direction of the curl, tells you like in what orientation this vector field is curling, right? If my vector field is rotating in this direction, then my curl is all going to be pointing. It's going to be pointing in this direction. Okay, and that's just because, as opposed to a divergence, remember before, the physical meaning of divergence here was basically how much is the stuff going in and out of a volume. There's no orientation there, right? And so that's why divergence physically is a scalar. Okay, whereas a curl is a vector here because there's actually an orientation for how this vector field is curling. Okay. Analogous to what we were talking about earlier with the divergence theorem, there is something called a Stokes theorem. Okay, and that's basically just the integral version of this that we wrote here. So that looks like this. It just says the surface integral of the curl is equal to this contour integral around a closed loop. All right, for an arbitrary closed curve where n is defined by the right-hand rule. Right-hand rule. Okay, cool. And that's basically vector calculus in a nutshell. That's basically all we really need to know, okay? So now you guys know how to manipulate vectors. Now you guys know how to manipulate tensors. You know a little bit about what curl is. You know a little bit about what divergence is and gradient and stuff like that. And now we're actually going to start to play a little bit in and think about how to use these things in fluid mechanics. Okay. Any questions so far on all the vector calculus stuff we've been talking about? How to manipulate them using index notation, et cetera, et cetera. Okay, there'll just be a couple more questions a little bit on this week's homework set, which I haven't posted yet. I'll do that as soon as I get back to my office. Still on vector calculus and some of these things that we just talked about today. Okay, but now we're going to get into actual fluids. Okay, still a little bit of math, but we're going to get through it pretty quickly. Okay, the first concept that I want to introduce is called a material derivative. Okay, for reference, I'll try and do this as we go along. I'll try and sort of, you maybe have seen so far that like we kind of loosely follow the textbook. There wasn't really like a section in the textbook that like explained index notation in the same sort of detail that we talked about, but hopefully the notes have been good enough and the TAs have been good enough that you guys have been able to follow along. Now we're actually getting into sections of the textbook that are explicitly linked to what we're talking about. So this is section 2.3 in the red Dean textbook. Okay. The question that we're trying to answer is, let's just say for a scalar field, or we'll say consider a scalar field that's a function of x, right? That's what a field is. And it's also time dependent. So it's a function of x and t. Okay. The question we're trying to ask is for an observer, moving at some velocity v, okay, how does f change? Okay. So in other words, what does the like if there's a, let's say a scalar field, we can call it a temperature field, okay? There's a temperature in this lecture hall that half of the class is virtually experiencing right now, where let's say that side of the lecture hall is really, really cold, and this side of the lecture hall is really, really hot, okay? And the overall temperature could also be changing. So the temperature is increasing also in this lecture hall by a factor of a couple degrees per minute, per hour or something like that, okay? And also, you know, that side is colder and this side is hotter or something like that. If I am a person, I'm walking around in this, what do I experience as my temperature as I move through this area? Okay. So what that means, though, to calculate this result, that suggests that there are two effects, okay, that we need to consider. The first is, as I mentioned, the temperature of the overall room could be changing, okay, or the temperature of the value of the scalar field could actually be changing over time. Remember, the scalar field f is a function of both position and time. Okay. So that is basically the change in f over time. Okay. This effect is independent of v. Right, and this is the easiest one, okay? So let's just say over some time t, some time interval delta t, okay? The contribution of this effect is df dt times delta t, right? That's very straightforward. It's just the time derivative, okay? Because f is changing with respect to time, and so that's it. Okay. The other effect is the fact that, well, I am moving in this room, right? And so there is some spatial variation that I'm going to experience as I move through the room. Okay. So if I'm going to ask myself over, again, we're talking about over a time delta t, right? How much do I actually move? Well, the observer moves an amount of delta x, which is just equal to v times delta t, right? That's, again, over a time of delta t, okay? And we've already talked about Taylor expansions or started using Taylor expansions and stuff, right? So if I want to know how much the field, the scalar field changes when I move a distance of delta x, well, that's fairly straightforward. So the question is, are we assuming then that the temperature changes constantly throughout the entire room? So in other words, like if like I move from here to here, the temperature goes up by 1 degree. Then if I start off here and then I move again over here, but then that goes up by a factor of 1 degree. Is that the question? The answer is no. Basically, it can be whatever. All of this is just a local. It's just a local effect. Okay. And so it's just if I start at some x, and then I move some delta x, then the Taylor expansion here suggests that the new value here is f at x and t plus, and we just talked about the gradient yesterday, right? Plus the dot product of the gradient times delta x. And so to answer your question, the gradient could be different at different locations in the room. And so not necessarily, so it's not necessarily if I just move one, if I move here, then I go up by 1 degree, and if I go over here, I go up by another 1 degree. If the gradient happened to be constant, then yes. The answer to your question would be yes. Okay.
Why is the first term in the Taylor expansion a vector field?
The question was, why is the first term in the Taylor expansion a vector field? And the answer is because I messed up. Okay. So I went ahead and deleted that. All right. And so what this means is that f changes by this quantity over a time of delta t, right? And of course, delta x is just equal to v times delta t. And so what I have is del f dot v times delta t. Okay? And so now all I'll have to do is just add those two things together. And so thus, the total change as delta t goes to 0 is the first thing, df dt, plus v dot del f, just because I switched the order of this. Dot product's commutative, so it doesn't matter, right? So what that suggests then is that if the answer to my question that I posed at the very beginning, for an observer moving at some velocity v, how does f change? Well, it'd be nice if I could just write it in terms of a derivative, right? You know, when a change in something is a derivative, and it's a special derivative. And that special derivative is called a material derivative. Okay. Sorry, my handwriting's terrible. I'll try and do better, but hopefully from context, you know that what I'm trying to write here is the word derivative. Okay. Some people also like to, some sources also call this like the convective derivative or something like that. It means the same thing. It says it's denoted by the special operator with a big D, and it's defined as basically this. Okay. And the physical interpretation of this is basically, this is the rate of change in some quantity as seen by an observer moving with a fluid. Now, I didn't actually explicitly mention fluids in here. The idea is just that the fluid has some velocity field v. Okay, and so if I'm moving along with the fluid, then it's that. Then that's what's going on here. Okay. Any questions on the material derivative stuff? It's just that when we start thinking about like, if I'm a piece of fluid or something and I need to think about like all the mass that goes in and out of me, we're going to talk about conservation of mass next during the next lecture. Or the amount of momentum or the amount of energy that's carried with my fluid, you just have to realize that the fluid is also moving. And so it's not just the fact that the overall temperature field could change or the overall velocity field could change. It's also how the whatever piece that you're in is actually moving along with the material derivative. Okay. Let me give you an example. Okay, and that's that fluids can accelerate okay. Because if we're talking about, so this is the material derivative, it's the rate of change in some quantity. We derived it for a scalar field, for some sort of scalar field f up here, right? But what we derive could also be applied to a vector field or even a tensor field or something like that, right? We just derive it 3 times to get to a vector field, right? Or we derive it 9 times to get it for a tensor field or something like that, right? And so if what we wanted to look at was dv dt, right? So how much does the velocity change if we're moving along with the fluid, right? Then that has 2 components, just like what we talked about, the two different effects. There's a dv dt, okay? And then there's a v dot del v, right? These are both acceleration, okay? This first bit here is an instantaneous acceleration. Remember, acceleration is the time derivative of velocity, right? And so this is the time derivative of velocity. But the point is just that because of this material derivative aspect here, we have 2 components of that. The first one is the instantaneous acceleration. That basically says, okay, if the whole velocity field is actually changing with respect to time, then let's say I have a water bottle here, and then I move it, right? Then the velocity field of all the water molecules in that water bottle is pointing in this direction, right? And then if that water bottle is in an accelerating car, right, then there's some instantaneous acceleration of all the water molecules in that water bottle, and it's moving in this direction, right? And you can calculate that by just taking the time derivative of that velocity field. Okay. The other aspect, though, is called convective acceleration. And what that says is that a velocity field isn't actually changing at all over time. It's steady, is what we like to call it, right? You can still have some amount of acceleration, right? For instance, let's say I have water moving through a channel like this. We haven't explicitly introduced conservation of mass, but maybe you guys can believe me that if I have fluid moving through here and it's incompressible, then the velocity has to speed up in order to go over here, right? And from what I just said, speed up, that's intuitively what we're trying to convey here, right? Because even though this is steady flow, in other words, the overall velocity is not changing, I'll call it steady contracting flow, right? Assuming you have a large vat of water on this side and an outlet here that isn't going to overflow, you can have this velocity field going for as long as you really want, right? So this field is steady, and the velocity vectors in this field are all going to be the same, right? That means dv dt equals 0 because it's steady, right? But clearly, dv dt is non-zero. Because as you said, and you guys can see this intuitively, right? If I'm moving along with this fluid, I'm clearly going to speed up as I move through here. Okay. We can do a mathematical example as well. All right. Let me give you a velocity field. Okay. So let's say the velocity field looks something like this. This is a capital letter omega. It's just a scalar. Okay, it's just a constant. Okay. Does anyone have any idea what that velocity field looks like? Something that will be helpful to you guys when you're, let's say, on an exam or you're doing your homework or whatever, and we give you a velocity field, or let's say you calculate a velocity field, is to have some idea of how to sketch those velocity fields. There's ways of doing it in MATLAB. I'll encourage you guys to do that at some point. I think there will be homework problems that actually show you guys how to do that, right? There are commands in MATLAB that can just draw out a vector field and stuff, but just by hand, something as simple as this, we should all roughly be able to figure out how to do this. Okay, so let's do that over here. Give ourselves a set of axes here, and here we're using x, y, and z just because it's a little bit more familiar rather than 1, 2, and 3. Just know that x is 1 and y is 2 and z is 3, right? Well, here's the origin. There's no velocity there because vx is equal to, well, y is equal to 0, x is equal to 0, and 0. So there's no velocity there, right? So I come over here, let's say to the point 1, 0, right? Then that means my vx is going to be 0 because my y is equal to 0. My vy is going to be in the positive direction, okay? Because x is equal to 1. So that means that my velocity field here is going to look something like that, right? And then the farther out I go in x, then the larger these vector fields, these vectors become, right? Similar idea up here. If I come over here, let's say x equals 0 and y equals 1. Then over here, y equals 1, so my vx is going to be negative. And my vy is going to be 0 because x equals 0. So I'm going to get something that looks like this. Okay, and then the farther out I go in y, then the larger these vectors become. Okay, I'm going to do these two axes, and then you'll see exactly what's going on here. Maybe you guys can already piece together what this vector field actually looks like. Okay, over here I have a negative 1, 0 or something. Okay, then my vy is going to be negative, and my vx is still going to be 0. So it's going to look like this. Okay, and then over here it looks something like this. And you guys can also look at the cases, for instance, over here, if I look at the point 1, 1, right, then I'm going to get something that's negative in x and positive in y, and so it's going to look like this. Whoops. Okay, and that's my vector field. Okay? That's in general how you draw a vector field. This will be a very important skill throughout this class, or just anytime you're dealing with vectors and stuff at all. It's just to be able to visualize how vector fields actually go. Okay? Now, if we want to calculate the acceleration here, then the acceleration looks like this. dv dt, right? That's dv dt plus v dot del v. Okay, now we know this first term is 0. There's no time dependence in this velocity field. Okay, but the second term here, we're going to have to figure out tensors and stuff like that. You know what? I kind of find that annoying. I'm going to do it like this. Okay, a sub j is equal to vi times del vj times dxi. Okay? That's how we write this second term in the next notation. Does this kind of make sense to you guys? Okay, so what that means then is that ax, or in other words, when j is equal to 1, is equal to vx times dvx dx plus vy times dvx dy. Remember, I sum over repeated indices here, right? So if my j is equal to 1, then my I still needs to be summed from 1, 2, and 3, and I drop the z because there's no dependence in the z direction. Okay, and likewise, ay is just vx times dvy dx plus vy times dvy dy. Okay? Yes? Why are we ignoring the instantaneous acceleration? Okay, so the question is, why are we ignoring the instantaneous acceleration? It's because there's no dependence on t anywhere here, right? So it's just equal to 0. Okay. Yes, in general, you can't ignore that, but in this particular velocity field, there's no t dependence, and so this term is definitely equal to 0. Okay. And so this is where index notation is kind of cool, right? You write an index notation, you don't even have to draw any matrices at all. You don't have to do any sort of multiplication or anything like that. All right, well, now we can actually calculate what these things actually are, right? So Vx is minus omega y, and dVx dx is equal to 0 because this does not depend on x. Okay, so this first term doesn't matter. Vy is omega x, and dVx dy is negative omega. So this gives you minus omega squared x. That should be an equal sign. Okay. And likewise, this one over here, dvy dx is equal to omega. dvy dy is equal to 0, so it's only the first term that matters. And then this is a negative omega y. So what I get here is negative omega squared y. Okay. And we can draw this. So this is the velocity field v, right? We can also draw what A is going to look like. This one's a little bit easier. AX looks like this, and AY looks like this. It just means everything's going towards the middle, towards the origin, right? It's linearly, the vector is linearly related to the position. And so what I get is something that looks like this. Like that, right? Which is maybe not a surprising result at all, right? Because, well, there's something called centripetal acceleration, right? You guys might remember from high school physics. That centripetal acceleration is related to the angular velocity squared times the radius, right? I use this capital omega here because the capital omega is basically angular velocity. The higher my omega, then the higher my velocity is going to be, okay? And so my acceleration is a vector. It's always pointing inwards, and it's equal to the angular velocity times x in this case, or y is basically the radius. Okay? Does that roughly kind of make sense to you guys? So that's going to be that's an important concept when it comes to actually looking at how things change when we deal with fluids. I have just a few more minutes, and so I'll just introduce very quickly a pretty simple concept that also helps us visualize fluids a little bit. And those are called path lines and streamlines. Traditionally, when I teach this class, I like to show a little video that actually shows what path lines and streamlines are. Because we're doing this sort of weird remote thing, it doesn't really make sense for me to just plot it, to just show a video. So what I'll do is I'll post a link to that video on Canvas and then have you guys watch it when you guys are at home. Okay. Basically, this is all about how do we visualize different flows. For instance, this is a potential fluid flow, right? The question here is just how do we visualize that in the most effective way possible. And there's just two different ways of doing that. One of them is called a path line, as you guys could probably imagine, right? Those are solutions. Oops. Those are solutions, time-dependent solutions of this equation. Okay. This is just a linear differential equation. It's a first-order differential equation. Okay, you guys could solve that, right? It needs an initial condition, and that initial condition is just that x is equal to x0 at a time t equals t0. What this equation basically says is that if I have a particle and it starts at a position x0 and it flows along with the fluid, what path does it trace out? That kind of makes sense? My x of t is going to be basically what's the path that traces out. That's why it's called a path line. Okay, this is the path of a particle released at a given position and time. Okay. The other concept that I'll mention is a streamline. Okay. A streamline, I'll say streamlines are tangent everywhere to my velocity field at a given time t. Okay. And so the way that works is I'm going to have some sort of parameter I'll call that P, okay, for some parameter P, okay? Don't worry about what that parameter actually is at this point. Just know that in this definition, these are lines, right? And the tangent of those lines is, well, by vector calculus definitions, that's just dx dp, right? Okay, and this just says that the solutions are tangent to my velocity field, okay? In the video that you guys will see what the difference between a path line and a streamline is. In many cases in this class, we're going to deal a lot in this class with steady flows. If the flow is steady, then the streamlines and path lines are identical. Okay. So just as a quick example, I think I have maybe just 2 more minutes. You guys remember this vector field that I introduced right here? Okay, let me just rewrite that right here again. If I have my Vx is negative omega y, my Vy is omega x, like that. Then to calculate, this is a steady flow, and so it doesn't matter what my path lines and streamlines are. I can basically then just find the solutions to this particular equation. Okay, to do that, I get dx dt is equal to Vx, which is negative omega y, and dy dt is equal to omega x. Okay, and this is just a set of 2 linear differential equations that I can solve to figure out what x and t, or to figure out how x and y depend on t. Okay. Does anyone happen to know how to solve a differential equation like that? It's just a system. It's a system of 2 differential equations. Both x and y could potentially be a function of t. Okay. The easiest way of doing this actually is to take the derivative of one and then substitute it into another. Okay. So d squared x dt squared. So the derivative of the first equation looks like this, like that. Okay, and because dy dt is just given by this, then this is just negative omega squared x. Okay, this implies that d squared x dt squared plus omega squared x is equal to 0. And you guys might know what the solution to this differential equation is. This is a second order linear differential equation. The solutions are just sines and cosines, right? So x of t is equal to a cosine omega t plus b sine of omega t. Okay, and by analogy, or I guess I can also figure out what dx dt is because dx dt is negative omega y from here, right? And so that allows me to figure out what y is. That suggests that y is equal to a sine omega t minus b cosine omega t. Okay? And if you go into MATLAB and plot what these lines would actually look like, can anyone guess what these lines are going to look like? They're going to look like circles, right? So the streamlines and the path lines are basically this. Which makes perfect sense, right? Remember when we plotted the vector field, they just look like they're going around a circle, right? And so the streamlines and the path lines are all this. Okay? So in the homework, you might see just one problem on how to actually figure out what these streamlines and path lines are and stuff like that. And then I'll encourage you to watch the video that I'll post a little bit later on campus for this. That we'll actually be using that site. It has a bunch of really nice videos that show you how to visualize flows and illustrate different concepts in fluids and stuff like that. And I'll refer to that a couple times. It's a set of videos actually from like the 1950s. And so you'll get a kick out of them because they're really, really old and they clearly look that way. Okay. Any overall questions before we wrap up? Yeah, in the back. So the question was, whenever we talk about steady flows, there's no instantaneous acceleration and the path lines and streamlines are identical, right? What you said is essentially correct. It's not because there's no instantaneous acceleration. The instantaneous acceleration is the concept that we're talking about for material derivative. The instantaneous acceleration is in contrast to convective acceleration and stuff. But it is true that when you have a flow that's steady, as we wrote here, then the streamlines and path lines are actually identical, right? And to explain that a little better, I'll make you watch the video first that actually shows like an actual particle moving along a fluid that's unsteady. You'll see what those path lines look like, and then you'll see what the streamlines actually would look like in that case too. Okay? One more question, sorry for all the Zoom folks, go ahead. Yeah, so in order to, so the question was, when we say that the solutions are x of p for some parameter p for streamlines, what does the parameter p mean, right? It doesn't really matter, is the answer. If I want to plot a line in space, I need to have a parametric representation of that line, and that's what the p is, right? It doesn't, I need to have x and y as a function of something, right? Just mathematically speaking. Now, in the path line case, it makes the most sense for that just to be equal to t, because it's as if I have a particle that's actually moving with some speed. When it comes to streamlines, I just need some parameter. I could have called it t, but then that gets confusing with this t actually, right? Because the streamlines could potentially be time dependent if the flow is unsteady, right? If at one point the flow looked like this circle, but then at another point, somehow the flow like warped into this converging flow, then the two streamlines are actually going to be different. Then the streamlines are going to be different at time t equals 0 versus some time t equals some time t in the future, right? So when we calculate streamlines, we always just hold this t to be fixed, and then we introduce some other parameter and solve according to that. Yes, yes. So what Borges was saying was that this is streamlines are basically at a given time t, and so I'll underline this bit right here. Streamlines depend on like the overall shape of the streamlines are different for different times during your flow, if the flow is unsteady, obviously. Okay. And again, the example, as I mentioned, is like you could imagine some sort of fluid scenario where like it's in a centrifuge, but then suddenly you're draining the centrifuge, like after you're done with your centrifugation or something like that. Right? then the streamlines during the centrifugation is going to look like this, but then as you drain it, it's going to look something completely different. Okay. All right, I think we're being kicked out of the room. Any sort of last questions? Otherwise, hold them all for Friday or something. Okay. All right, thanks a lot. See you guys later.
Thank you. Bye.